Disha, can you hear me?
Yes, sir, I can hear you.
Yeah, okay. Okay, in the Python console, you can type these instructions, and let us try to understand what their meaning is. Okay, so we have something called as the bitwise operators, which can be applied only on integer values. They cannot be applied on float values. Okay, so I'll be doing it here. Let me take some values. I is equal to, let me restrict to 4-digit numbers. Okay, let's say I is 13. Okay, then j is equal to uh, let's say 8. Okay, can you obtain the binary equivalents for I and j? How do we display, how do we get the binary equivalent value of 13 and 8? Try to remember, we did conversions at the end. What function can you use? Can you see my screen?
Yes, sir.
Okay, it has the answer then.
Sir, I couldn't hear the question.
Like, how do I get, suppose I have I as 13 and j as 8. I want to write them in binary form. I want to get their binary equivalent.
You have to divide them with their positional weights.
No,
No,
but
we have to
there
divide
is a
them by
built-in
2.
function. No, there is a built-in function that does that. You don't need to really compute. Python already provides you a feature which shows integer value in a binary form. Can you tell me which one? Disha,
Disha left the session, sir.
is it?
Yes,
Okay,
sir.
that was changed. Disha,
Can you hear
hello.
me? Yeah.
Can you, Disha, can you hear me?
Yes, sir, I can hear you.
Yeah, okay. So we can use something called as the binary of I. Okay, bin of I. See, 13 is displayed in the binary form 1101. Okay, likewise, if I give bin of j, okay, it is 1000. Okay, in binary. So what these bitwise operators perform? Okay, so we as I have shown here, we have several bitwise operators, bitwise and bitwise or bitwise XOR, left shift, right shift, and the bitwise complement. Okay, so let's try to understand what those values are, so that we can understand their operations. Okay, let's do I and j. So this symbol, single ampersand, is called as the bitwise AND operator. Okay, bitwise AND. So now let's see the result of I and j. Okay, it says result of bitwise I and j is 8. Okay, when I perform a bitwise AND on 13 and 8, the result is going to be 8. So let's try to understand what's the meaning of it. Okay, so I have two values, 13 and 8. 13, which is represented as 1011, yeah, 1101, sorry, 1101, and 8, which is represented as 100. Okay, I think you can understand why 13 is represented as 1101. Okay, this is 2 into 0, 1, 2, 3. Yeah, 1 into 2 power 3 plus 1 into 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0. If you add them, it becomes 13. Okay, 13 in binary is 110. 8 is 1 followed by 3 zeros. So now we are performing a binary and bitwise and operation on it. Okay. So for that, we have to form a truth table. You are aware of truth table things that logic that has been taught in your class, oppositional logic.
Hello?
Hello. Yeah, Disha, can you hear me?
Yes, sir. Uh,
Yeah.
I can.
Okay. So you are following, right? Whatever I told so far.
Yes, sir.
Yeah. Okay. So we have to understand the truth table for bitwise and. Okay, if it is 1 and 1, the result is 1. If it is 1 and 0, the result is 0. If it is 0 and 1, the result is also 0. 0, 0, 0. Okay, so this is the rules. Okay, so uh, okay, can both of you hear me, Tanmay and Disha?
Yes, sir.
Yes, sir.
Yeah. Okay. Okay. So we have to use this rule. Okay, this truth table. Okay, if both inputs are 1 1, the result will be 1. 1 bitwise and 1 is 1, and 1 and 0, 0 and 1, 0 and 0 are all the results is going to be 0. Okay. So now let's apply that result here. So according to a truth table, okay, let's compare bits at the corresponding positions. Okay, so what is 1 and 1? 1 bitwise and 1 is how much? According to our result
1,
table here, 1. Okay,
1,
1 and 0.
0,
1 and 0 is 0. Okay, 0 and 0.
0,
Okay, 1 and 0.
0.
0. Okay, so when we perform a bitwise and, then the result will be of this form. So unlike our earlier operation, suppose I said 13 plus 8, the operations were done as a whole. Okay, on the whole values, 13 plus 8 was added, not on their binary representations. But these bitwise operators perform operations at the bit level. Okay, so we have to take their binary representations, and then uh, we need to understand how it works. Okay, once we have understood this logic, you don't need to do the computation every time. You can just say, okay, this is how the bitwise operator works. Okay, uh, so let's take a slightly different value, uh, say 23. and let's say 17. Okay, let's perform the can you tell me what is the bitwise equivalent of binary equivalent of 23? Use your Python shell and let me know how do I obtain the binary equivalent of 23. Can someone tell me the result?
1 second, sir.
Sure. I had some network issues, so I could not hear what you were talking earlier. So could you
Okay,
explain how the
sure,
bitwise
sure.
works?
Yeah, bitwise and suppose say I want to perform an operation called I and J. Okay, here this is how we perform a bitwise and. So let's assume that I has a value 13 and J has a value 8. Disha, you are hearing me, right? I'm audible.
Yes, sir. I can hear you.
Yeah. Okay. So 13, you have to write it in the binary representation. Okay. So we have a way to find out the binary representation. See, like bin of I contains 13. Binary of I, it gives me this value 1101. Okay. The prefix 0b is saying that it is a binary value. So equivalent of 13 is 1101. Okay. So this is how you get the binary equivalent of any particular number. So if I want to get the binary equivalent of J, what should I do, the Disha then?
Bin of J.
Right? Yeah. So bin of J we have done that and we have found out that the equivalent of J, which is 8, is 1 followed by 3 zeros. So I have written that here. Those two, 13 is 1101, 8 is 1 followed by 3 zeros. So bitwise operations happen between corresponding digits. Okay, with this one, this zero will be compared. Okay, and so on. So what is the rule for bitwise and? Like if both the bits are ones, the result is 1. Otherwise, if at least one of the bits is 0 or both the bits is 0, in all those cases the result is 0. Okay, so we are applying this truth table or rule here. So 1 and 1, the result is 1. 1 and 0, second position, 1 and 0, result is 0. 0 and 0, result is 0. 1 and 0, result is 0. So the resulting value is 100, which is 8 itself. Okay, but don't make a generalization that when I perform bitwise AND on two numbers, the result will be the second number. That need not be the case. Okay, so maybe instead of 8, if I had 9, okay, then it would have been 1001. Uh, Sorry, not that, not 9. Let's take 10. Okay, 10 would be 1010. Okay, in which case the result would have been 1. No, this would also give me zeros. Mm, Now let's see a different example later. Okay, what I'm trying to say is that the result always need not be the same as the second number. Okay, maybe this example should have made it. 0101 is 1 2 4 4 5 5. 5 and 10 would give me 100. 0. 5 and 10 would give me the result as 1. Okay. Uh, did you understand this particular part as to how to perform bitwise AND operations?
Yes,
Yes.
sir.
Yeah. Okay. So let's verify this whether it is the case. So I assign I is equal to 5. j is equal to 10 if I perform I and j. Okay. So did I do the computation somewhere wrong? Oh, 10 is not 1001. Sorry, that's 9. This is not 10, this is 9. Okay, 5 and 9 should give me a result. I is 5, j is 9, j is equal to 9, uh, and then I and j, I and j will give us the result as 1, okay, which we have verified here. Like that, find out 23 and 17 and tell me the result. What is I and j if I were to be 23 and j were to be 17? I is equal to 23, j is equal to 17. I and, so to find out the value, you would run I and j. What is the result of I and j? Bin of I bin of j I and j gives you 17 itself back. Are you getting this? Hello?
Yes, sir.
Yeah, are you getting the same? Okay, so this is how the bitwise AND operation works. Okay, so this is typically used when we work with hardware circuits and all. Okay, later we will have a look at things where we need to test whether a particular switch is on or something like that. In such cases and all, we use such bitwise operations. Okay, so in case of bitwise, the next operator, okay, the single pipe symbol, okay, to type it, you have to use shift and press the key above enter. Okay, the backslash. If you press with shift, you will get that pipe operator. So the bitwise, so let's see how bitwise and OR works. Okay, bitwise pipe. In which case, here, if at least one of the inputs is 1, the output is 1. Otherwise, if both are 0, then the output is 0. Okay, this is the rule for bitwise OR. So, tell me what is the result of 23 and 17, bitwise OR of 23 and 17?
Sir, I couldn't hear you for a second. Can you explain the OR function again?
Bitwise OR. So the rule table is this one, the highlighted one. Okay. So if both the inputs are ones, output is 1. If one of the input is 1, then also the output is 1. Only when both inputs are 0, then the output is 0. Okay, in the bitwise AND, when only both inputs are 1, the result is 1. In all other cases, it is 0. Here, in bitwise OR, only when both of them are 0, then the result is 0. Otherwise, the result is 1. Did you understand this, Tanmay?
Yes, sir. Yes, sir.
Yeah, okay. So find out 23 and 23 bitwise or 17. What is the result of it? I pipe j. Okay. The pipe operator stands for the bitwise or operation. What is the result of I or j? Bitwise I or j. Disha?
Sir, I'm not getting anything. I'll just try again.
Huh. Not getting as in not able to see the screen or like
No, it was just
huh?
empty in the console. So I'll just try
Uh,
it again to check if there's anything wrong.
okay, see like can you see my spider console here? Can you see my screen?
Yes, sir, I can see it.
Yeah, so this is where you are supposed to run. Okay, j is equal to 17 I pipe j.
Sir, I
Yeah, I
got
got
10111.
Which is decimal. Yeah, so in decimal, what is that value equal to?
23.
23.
Okay, yeah. See, I bitwise rj is 23. Okay, let's take another set of values. Okay, let's take one even number and odd number. Let's say, no, let's take the value 26 and 35. Okay, find out the bitwise r of 26 and 35.
59.
I is equal to 26, j is equal to 35. Oh, what did I say? 35. Yeah, 35. Okay, so binary of I, binary of j. Okay, so here when you want to do this binary operations, 26 has only 5 digits. Okay, whereas 35 has how many digits? 6 digits. So to make them of equal length, what you can do is you can add a leading 0 for 26. So it becomes 011, 010, 100, 011 for 35, and then the corresponding bit operations would be performed. So I or J will be 59. Okay. So bin of 59 is this. So you can compare 0 or 1 is 1, 1 or 1 is 1, okay, 0 or 0 is 0, 1 or 0 is 1, and likewise. Okay, so the this last one will be compared with the leading 0 here, and that is also 1, 0 or 1 is 1. So this becomes the 59. Okay, that is how bitwise OR will work. Okay. Next is, let me write the names also here, and shift or control C. This is called bitwise and this is called bitwise OR. Okay. Next we have bitwise XOR, the cap symbol 6. Shift, if you press 6 with the shift key, you will get that XOR operator. Okay, we call it exclusive or in short XOR. Okay, so the truth table is different here. When inputs are similar, the output is lower, which is 0. When inputs are dissimilar, okay, 1 0 and 0 1, then the output is high, which is 1. Okay, this is the truth table for bitwise. So the property of bitwise is that if both the inputs are same, okay, 1 1 or 0 0, the output would be 0. If the both inputs are dissimilar, one being 1, another being 0, or one being 0, another being 1, the output is high, which is 1. Okay, this is how bitwise XOR operation works. Okay, so which are the values? 26 and 35. Perform a XOR and let me know what is the result of bitwise XOR.
57.
I XOR J. Okay, 57. Okay, so we can do an interesting thing with this bitwise XOR. Okay, so first let's see what are the values of I and J. Okay, they are 26 and 35. Okay, execute these instructions with me. I is equal to I XOR J. J is equal to I XOR J. I is equal to I XOR J. Okay. Execute these statements and find out the values of I and J after these three operations, and tell me what did you observe. I is equal to I XOR J, J is equal to I XOR J, I is equal to I XOR J. Three operations.
The values of I and J are interchanged.
Yeah, they get swapped. This is another way of exchanging or swapping values between variables. So if I print I and J, it is 35 and 26 now. Okay. So earlier we had learned a method of swapping the values. How do you swap those values? What was the first method? Simultaneous assignment. Do you remember?
Yes, sir.
Yes,
Um,
sir.
Uh, how would you do that?
X comma Y is equal to Y comma X.
So in case of I comma j, if I want to swap the values, what should I do?
J comma is equal to J comma I.
Yeah, that's what. Same thing. Like I comma j is equal to j comma I. If you do this also, values of I and j. See, I and j earlier were 35 and 26. After this operation, it becomes 26 and 35. Okay. So these are two ways of swapping values. Okay. So this is how XOR operation is used. Okay. Uh, then last, what else we have? Okay, we have something called as the shift operation. Okay, left shift and right shift. So here, earlier we were saying these two are the operands. Okay, we are applying bitwise AND on I and J. Okay, but in case of left shift and right shift, okay, so if I say I left shift J, so it should be read as shift I by J positions to the left. Okay, so let's try to understand what this means. Let's say I is equal to some value 33. Okay, can someone calculate and tell me the binary equivalent of 33? In your console only you can run the binary operation and tell me what is the binary equivalent of 33.
10001.
10001.
1.
Yeah, 2 power 5 is 32, 32 plus 1, 33. Yeah, right. Okay. So this is the binary equivalent of I. Let's
Sorry,
say,
sir. There's 4 zeros.
huh?
There's four
Yeah, okay.
zeros, not 3.
Four zeros, four zeros. Yeah, yeah, yeah. Right. Okay. 2 power 0, 1, 2, 3, 4, 5. 2 power 5 is 32, 32 plus 1. Right. Okay. So let's say j is equal to 1. So now, if we do I left shift j, so we should read this as shift 33, shift the bits of 33 by one position. So j should be read as positions by j positions. In this case, j is 1, so I will say that shift the value of I, shift the bits in I to the left by 1 position. Okay, and add a 0 at the end. So what happens is, like, this one gets shifted here, 0 shifts here, and so on, and the resulting value will be 1 followed by 4 zeros, 1 and a 0. Okay, let me show you this. Control C, here, Control V, uh, Control V. So each of these values, okay, gets shifted by 1 position to the left. This one in the new value becomes the second last digit. Okay, and at the end, okay, I have shifted by 1 position, so I'm adding a 0. Are you able to see this?
Yes, sir. But can you
Yeah,
repeat it again?
yeah. So I'm doing shift of I to which direction? Left direction. By how many positions? One position. So shift every. So if this is the value in I, take every bit of I and shift it by one position. So here one was the last bit. Here it is the second last bit. This 0 is the second last bit in the initial value. It is the third last bit, and so on. Okay, and at the rightmost end, after shifting, there was a vacancy created that will be filled with zeros. Okay,
Okay, sir.
so can you convert this back to decimal and tell me what is that value? 1 followed by 4 zeros and then 1 0. How do you convert binary into integer? Control C. C 0 B. Okay, this is equivalent to the value 66. So now, what was the initial value of I?
33.
33. After a shift by one position, what did I get?
66.
66.
66. How is it related to 33?
Double of 33.
It's double. Okay. So shifting by one position means, okay, you are increasing it by a power of 2 or multiplying it by 2. Okay. Suppose I do I left shift by two positions. So what value would I get in that case? Shift every bit by two positions. And how many zeros should I add at the end?
We should add 2 zeros in the end.
Two zeros. Because two vacancies would be created because we are shifting it by two positions. So you would get two zeros.
132.
Okay. So this would be the result. So in other ways, shifting left by 2 is also the same as multiplying by 2. Okay. So if I have I is equal to 35, okay, I star 2 and I left shift by 1, both of them give us the same result. Okay. But look at the computation. Which one is more easier in calculating? Suppose I ask you to multiply 35 by 2 using this method, okay, and this method. Which one is simpler?
Left shift.
Left shift. Why? Because you don't really need to do any new computation. Just existing bits, you just shift, and at the end, whatever vacancy is created, you just need to fill it with zeros. Okay. However, in case of the multiplication, you have to do 35 into 2, 5 to the 10. So give 1 as carry, 3 to the 6 plus 1, 7, and such things. Okay. So whenever you want to do multiplication by 2 in a much faster manner, you can go for left shift operations. Okay. Instead of doing a multiplication. Okay. So if I do I left shift by 2 positions, what is it same as? Hello?
Into 4.
Into 4. What about 3?
Into 5, no,
Into
into
6.
6.
No,
6.
into
So
8. Into 8.
8. So
Okay.
what is the relationship you are seeing here? Okay, every shift is equal to a power of 2. Okay, 1 is 2 power 0. Okay, 2 is 2 power 1. 3 is sorry, 2 is sorry. When I left shift by 1, it is equal to 2 power 1. Whatever left shift operation you do, just calculate the power of 2. Okay, 2 power 1 is 2. So it is multiplication by 2. If the left shift is by 2 positions, 2 power 2 is 7. So left shift gives you multiplied by 4. If the left shift is by 3 positions, it is the value gets multiplied by 2 power 3, which is 8, and so on. Okay. So every time you shift one position to the left, you are increasing the power of 2 by one position. Got it? Hello?
Yes, sir.
Yeah? Okay,
Yes, sir.
fine. So similarly, we have right shifts. So right shift does the opposite thing. Okay. So it shifts the value to the right. Vacancies are created on the left hand side, where we put zeros. Okay. However, anything that goes beyond the right side, they are discarded. Okay. So let's see an example of it. So I binary of I. Okay. I right shift by one position. BIN of 17. BIN of I. Okay. Can you see these operations? Okay. So when I do I right shift by one position, I's value was 35. When you do a right shift, yeah, we get the value of as 17. So how is that? So we have 1 followed by 3 zeros and 2 ones. Let me show it on the notepad here. The value 1 followed by 3 zeros and 2 ones. 0, 1, 1. Okay. So what we have to do here is we have to shift every bit by one position to the right. 1. Okay. So this second last one comes to the last position, and this last bit, okay, this will be discarded, and we add a leading 0 at the end, at the leftmost end. We added zeros at the rightmost end in the left shift operation, whereas in case of the right shift operation by one position, okay, so every bit so these bits got shifted by right by one position. The last bit is discarded. Whatever vacancy is created at the beginning, you add a 0. Okay. Suppose let's say I perform left shift by two positions. What would be the result? So the first four bits will be copied. Okay. and then whatever are the last two bits, they get discarded, and we add two zeros at the beginning. Okay, so this is right shift by two positions. So let's take the value of I to be 35. I right shift by one position is 17. I right shift by two positions is 8. So do you see any relation between these values when we do right shift?
Their divisions of integer divisions of
Of
each number of
integer
2
division by 2, okay,
by
or
2.
powers of 2. Okay, so I right shift by 1 is divide 35 by 2 but perform integer division. Okay, so 35 by 2 is 17.5, but we are interested only in the integer part, so we get 17. If I divide 35 by 2, I get, sorry, 35 by 4, I get it to be 8.5, but discard that and we are left with only 8. Okay, so if you want to perform integer division by 2, you can use a right shift operation instead of the actual integer division by 2 operation. Okay, and last one is the complement. So for complement is a unary operator. Okay, so can you see the highlighted portion here?
Yes, sir.
Yes, sir.
Yeah. Okay. So all these operators, so for bitwise operators, require two operands for them to operate. Okay. So that's why these bitwise operators, bitwise AND, OR, XOR, left shift, right shift, they are called as binary operators because they require two operands. However, this one is actually the unary operator. It requires only one operand. Okay. Negation works only with a single value. So bitwise complement, we call it as bitwise complement. Okay. So bitwise. So the to type that symbol, okay, you have to press shift and the key above your tab key. Okay, just before one you have a key. Okay, it has a wave kind of a symbol. Okay, that's the bitwise complement. So because it is a unary operand, okay, if the bit is 1, the result will be 0. If the bit is 0, the result will be 1. Just complement. Okay. So this is also called as bitwise complement. Okay. So let's take the value of I is equal to something, let's say 87. Okay. And then we perform a bitwise complement of I. The result that we get would be minus 88. Okay, so bin of minus 88, bin of 87. So in 87, wherever you are having ones in its binary complement, you get it as 0. Okay, so wherever you have zeros, you are getting 1 here. So that is the bitwise complement. And we have two other data types. called two other values which is a new data type. So far we discussed integer types. Another type is called as the Boolean type. Okay, so let's look into the Boolean type. So x is equal to the Boolean values are these. Okay, so when you type true, t should be capital. The same way, so there are two possible values, false and true. Okay, so I is equal to 13. So type of I is of which type? Can someone tell me?
Integer.
Integer type. Yeah. So do the same for x now. X or y. Type of x. What is the type of x? Anyone got this?
Bool.
Yeah. Okay. So they are Boolean types. Okay. So if we store either the value true or false, okay, then they are treated to be of type Boolean values. Okay. We use this to indicate the truthness or falseness of a statement. Okay. So sometime let's say I plus okay, I is there 13. Okay, I is it less than 25? If I say is I less than 25, the result will be either true or false. In this case, because 13 is less than 25, the result is true. Okay, this is the example of a Boolean operation. Okay, so and this less than is a relational operator. I will come to that shortly. Anyway, you know that it has the same meaning as in maths. Okay, and you can use the logical and. Okay, so you have to understand that this bitwise and is different from the logical and here. Okay, so for that, if x and y are two Boolean variables, then you can say you can perform a logical and x and y. Okay, so in our case, x was true and y was false. So AND operation will be true only when x and y are true. In all other cases, it is false. Okay, say I make this time y is equal to true. So x comma y both are true. In this case, if I do x and y, okay, we get the result to be true. Likewise, we have or and not. If I set y is equal to false, again y is equal to false, we know that x is true, y is false, x or y is true. So in logical OR, if at least one of the values is true, the result is true. Okay, it is false only when both the values are false. Suppose say I set x2 or x also as false. Okay, x comma y both are false. In this case, x or y is false. Okay, we don't have any logical XOR or shift operations. Okay, we have only logical and logical OR and a logical NOT. Okay, so if x is false, NOT of x would be true. Okay, if y is equal to true, y is equal to true, NOT of y will be false. These things are pretty much used when we write conditional statements later. Okay, selection statements. After discussing these types, we will move on to doing selections. Okay, where we are supposed to write conditions. Like for example, I want to test two conditions, and I want something to be done only when both the conditions are satisfied. Then I will use and. If condition 1 and condition 2, then do something. If say you say that perform something even if at least one of them is true, then we will say if condition 1 or condition 2, do something like that. Okay, so that we will look into selections. uh, yeah, so we saw about integer types. Next is floating point types. How do we represent decimal values, points that have something after the decimal point? Okay, so we have two data types, float and complex, and another called as the decimal dot decimal. They do not, it is not readily available. You have to import it. Okay, and when we store values in Python, the values are not exactly stored. It depends on the kind of value being stored. Okay, if the value can be represented exactly as a power of 2, it can be represented exactly. Okay, because binary representation is nothing but representations in base 2. So let's see that x is equal to mm, like x is equal to 1 by 3. So somewhere did I write it in exactness? Okay, I will come to this inexactness later. I will give an exact actual example for that. Okay, how the values are stored approximately rather than absolutely. Okay, so we can convert these float values. Suppose say x has a value 1.3. I can how can I obtain only the integer portion of x? What function should I use?
Sir,
Tanmay,
hello.
how do I obtain the integer portion of x?
Int x.
Int of x. Int of x gives me the integer portion of a float number. Similarly, I can have another conversion function. If I want to convert this float value to a string, I can say str of x. So 1.3 gets converted to string 1.3. 1.3 within double quotes. Sorry, single quotes. And likewise, you can convert a string value to a float value as well. Float of something 56.78. If we apply the float function, it gives us the equivalent floating value. Okay. Now type this along with me. Import sys. Okay. Sys dot float info. Are you getting this kind of an output?
Yes, sir.
Okay. So this says like what is the largest number that you can store on your computer? Okay. So it is 1.797 something multiplied by 10 power 308. Okay, you can imagine how big a number that is. Okay. So for example, I give 2 power 100. Sorry, this is x or not. 2 star star 100. Okay. Even you can represent that value also. So Python can really store large numbers. Okay. And what is the smallest value that you can store is stored in the epsilon. Okay, 2.2 multiplied by 10 power minus 16. You can imagine. Minus 16 means almost 15 zeros after the decimal point. Okay, and so on. So this is with regard to the range of the float value. You can further explore the details, okay, by using the help function. Help sys dot float info. The same thing that you typed, just type it within the help menu. So it tells you about what are there. Okay, what is the meaning of all the fields with regard to this particular value sys dot float info. Okay, so sometimes, okay, as I said earlier, the computation is not exact in case of float values. Okay, so say for example, if I do the calculation of a pi 22 by 7, okay, so the result that you are getting here, is it an exact value? Can someone tell me, is it the exact value of pi?
Yes, sir.
No, sir.
Why do you think it's not?
Sir, because pi has infinite number of
Yeah,
digits.
pi is a recurring decimal, right? So it keeps on going continuously. So this has done up till a particular precision. Okay, like how many? 3, 6, 9, 12, 15 digits of precision. It has given us only 15 digits of precision. Sometimes, okay, we would want the precision to be even more higher than what is given by float. Okay, so in such cases, we go for another data type called as decimal dot decimal. It provides us higher precision. Okay, means you can have more values after the decimal point, and also it gives you a much larger range than float. Okay, you can even store much larger numbers that cannot be stored in a float value. But there is a catch. Okay, because it provides you higher precision, the calculations are comparatively slower when compared to float. Okay, when you are multiplying two decimal dot decimal numbers, it may take more time when compared to multiplying two float values. Okay, where we use it, so any scenario where you think precision is of more importance, then we use decimal dot decimal in our computations. Okay, example could be a financial calculation or a scientific calculation. Okay, let's see how to use that. uh, so see, float, you don't need to import anything, it is available by default. But dot decimal is not the case, so you have to say import dec- decimal. Okay, if you are you getting an error in this case, or are you getting an empty prompt?
Sir, empty prompt.
It means that
Empty,
it is
sir.
working. Yeah, it's working. So your Python supports this data type, otherwise you have to install it. So import decimal dot then we can say x is equal to decimal dot decimal of some value that you want to store. Let's say I want to store the value of pi. Okay, y is equal to 22 by 7. What is the type of y now? Data type. How do you find out the type of a variable?
Type y
Yeah, so type y. What is the result of type y?
float.
Float. Okay, if you don't specify anything, if the value resulting value is a decimal value, 22 by 7, I get a decimal value, then y will be taken as float. Okay, so let's print the value of y, and x here also stores 22 by 7, but not in float format, but in the decimal format. Okay, so if you want to create a decimal value, you have to use the syntax the variable is equal to, and then you have to write package decimal dot decimal. Okay, this is an object of type decimal belonging to this lowercase decimal package. Okay, so let's print the value of x. What do you observe with regard to the values of y and x?
X has more. X has like X has more value
A
than
larger precision,
larger.
larger
Yeah.
precision, larger many values after the decimal point. Okay, so if required, you can use this particular decimal package to get higher precisions. Okay, another thing is constantly when you do programming, you try to do some commonly performed mathematical operations. Okay, like for example finding the sine of an angle. Okay, or you want to do a conversion from radians to degrees and so on. So for instead of every time, or let's say if calculating the square root, so instead of calculating this every time on our own, rather all of these are provided as functions. Okay, so for that to happen, we have to import a special library called import math. Okay, do this import math, and let's say I want to find out the square root of 13. Then math dot sqrt of 13. If you want to find out the square root of a value, you have to use the method called sqrt. Okay, do it along with me. What is the result?
Sir, it's 3.60
Yeah, yeah,
127
yeah. Okay, okay. So if you want to calculate the square root of a value, what will you do from here, from now on?
Use import math.
First, we have to import the math library, and then in the math library, we have a method or function called as sqrt. How to call that sqrt? We have to say package name. Package name is math here. Dot, and the method name is sqrt. And later, whatever value you want to find out the square root, you have to enclose it within parentheses. Okay. Next, we have something called as the floor function. Math dot floor. Okay. What does this perform? Disha, what is the result of bar dot floor of 9.3?
Uh,
So I'll just check. Yeah, it just doesn't. Nine.
Okay. So what do you make of the floor function?
We
Uh,
get the integer value.
Integer value. Okay. Uh, what integer value? So floor function always gives you the nearest integer that is smaller than the value given. Okay. So for 9.3, there are two integers that are closer. One is integer 9, another is integer 10. But among them, always it gives the lowest integer. Okay, so floor gives the lowest integer, or in other words, it is like you want to apply a round down function. Okay, then you can use the floor operator. Okay, mat.floor gives you 9. Even if I give 9.9 also, the result will be 9 itself. Always it will round it down. Okay, complementarily, like instead of floor, we have a ceil function, CEIL. So what is the result of the ceil function on 9.9?
uh, that is
CEIL. Okay, it is spelled as pronounced as CEIL,
Sir, it gives the nearest integer value greater than the number given.
greater than the number. Okay, so always it performs a round up operation. Okay, when we are doing a rounding of approximation operation, you have studied approximation, right? In maths. Hello.
yes,
Yes, sir.
sir.
There, what is usually done is zero point 0.5 and above gets approximated to the upper value, and anything below zero point 0.5 gets approximated to the lower value. Okay, but here we have two different things called as floor and ceil. Okay, so if you want to find out the smallest integer closer to a particular float value, you use the floor. If you want to find out the closest largest if you want to find out the closest integer that is larger than the float value, we use the ceil function. Okay, so even if I give math.ceil of 9.1, it gives me 10. Okay, and we also have an approximate function called as round. Math.round of 9.1. Okay, tell me what is the result that you are getting of round?
9.
9. Okay, I think it's caps round or no, round is not there. Huh? 1 minute. Math has no attribute round.
Sir, I got an
I
error.
think, yeah, okay, in the newer version they have removed round, I guess. Or we have a round function itself. Oh, okay. Round has been made a generic function. Okay, it's no longer in the math. Okay, they have made a change. So you don't need to do math.round. Okay, you can just directly use round. What are you getting for round 9.1?
9.
9. Suppose if it is 9.7, round 9.7, what is the result? Huh?
10. 10.
It's not 9. Okay, it's 10. What about 9.5? Tanmay?
10, sir.
Then what about 9.4?
9.
9. Okay, so from point 1 to point 4, it performs a round down operation. For 5 to 9, from point 5 to point 9, it performs a round up operation. Okay, or a regular approximation. Okay, then we have truncate also. Math dot truncate of 4.6. So truncate simply removes the decimal part. Okay, whether it is 4.6, 4.9 or 4.1, it is simply going to truncate. That's why it's called the truncate function. It is going to remove your fractional part. This is the same as doing int of 4.6 will also give you 4. Okay, then you can perform your trigonometric operations. Okay, math, and we have something some of the built-in constants also available in math. So if I type math.py, what are you seeing here?
Value of pi.
The value of pi. Okay, so you don't need to remember the value of pi now on. Okay, so if you want to use it in your computation, let's say I want to do 6 into pi, I just have to write 6 star math dot pi. Okay, and pi value, so in which measure is the pi value displayed here? Is it in radians or degrees? Pi value 3.14. Is it in radian measure or degree measure?
Radians.
It's by default, it is in radian measure. Okay. So let's say I want to find out sine of pi by 2. What is sine of pi by 2? Sine 90 is how much?
1.
1.
1. Okay. So if I have to find out sine, okay, I have to type math dot sin, math of sine of math dot pi. Pi also I have to extract it from the math library by 2. Okay. So if I want to perform sine of 90, if I give this way, it is wrong. Okay, why am I getting 0.89 here? Why do you think so? It thinks that this 90 is not 90 degree but 90 radian. Okay, anything that you give here should be given in radian measure. Okay, got it? Hello?
Yes, sir.
Okay, so whenever you want to calculate the sine of an angle, the parameter to the sine should be in radians and not degrees. Okay, like that, try to perform some other calculation, find out uh, cos 60. Which one is zero point 0.5, cos 60 or cos 30?
Cos 60.
Okay, for verify that, are you getting cos 60 as 0.5? Tell me, how would you compute the cosine? Hello? Hello, Tanmay? Hello? Tanmay, are you there? Hello? Disha, can you hear me?
Yes, sir, I can hear you.
Yeah, okay. Tanmay, hello.
Sir, can you hear me now?
Yes.
Hello, sir.
I wanted you to calculate and show me math dot,
Sir, I can't hear
sorry, the
you.
cosine of 60. Hello?
Hello, sir.
I can hear you clearly. I can hear you clearly.
Sir, my screen is loading.
No, you're already logged in. I see here that you're already logged in.
Sir, can you hear me now?
Yes, I'm hearing you for all the time.
Oh, okay, sir. I couldn't hear you. Can you repeat the question?
Calculate cos 60 and find out the result. How do you do that?
Sir, we cos 60 is
Type and do. Try it out.
yes, sir. Sir, cos I got a error. 1 second, sir.
So I got
Look,
0.5 followed by
ah,
lots of zeros and then 1. So,
yeah. See, the computations are not exact actually, especially when the decimal values are involved. So if you are getting a closer value, that's fine.
Sir, I got a error. Can I try again?
Huh. What is the error? What is the error?
A syntax error, sir.
What? See,
Math,
look at the example. Math. What do you
math,
type?
math
Huh.
dot cos
Dot.
9
Cos. Cos.
60 60.
Should you give 60? What did you listen then?
Oh,
The
sorry,
input
sorry.
should be radians.
Yes, yes, radian.
Radian measure. So
Yes,
how should I give it in radian measure? Express
mm,
60 in terms of pi.
yes, sir. Sorry, sir. I skipped that part.
So how should I write that?
Math dot pi by 2.
Is it math dot pi by 2? Pi by 2 is
No,
90, not 60.
pi by pi by 2, pi by 3.
Pi by 3. Okay. So you see that the result is 0.5. Okay. So whenever you want to compute a sign in your program, let's say you are supposed to um, uh, where should we use a sign? Can you tell me some formula in your physics or somewhere where you used a sign? Some example, maths or wherever. Any one of you, Dhanmai, Disha, some formula that has a sign in it.
sine square plus cos square is equal to 1.
No, like in a computation.
Ah,
For
okay.
example, let's say I want to find out the displacement of a body traveling at a velocity v or something like that. Then I use s is equal to half at plus something 80 square, something similar formula that has a sign in it as part of a calculation. Do you remember?
Sir, range formula?
What is it?
Uh, 2 into initial velocity sine theta into initial velocity cos theta by
So,
g.
yeah. So what computation are we doing there? Find the
Find range.
range. Okay, yeah.
I have a
So
easier formula also.
yeah. So yeah, let's say that we want to do that computation in a program. Okay. So we give all those values as input, and I want to find out. Then in your computation expression, like how we found out the area of a circle. Okay, here similarly you can use sine of an angle and so on. Okay, so maybe I will give you few assignments where you can try those things. Okay, write it in your programs. Then you want to find out the inverse. Okay, sine inverse, cos inverse, and all. Then we have something called as the arc sine or arc cosine and so on. Okay, so for that I have to write math dot a sine of 1. Okay, what is sine inverse of 1?
Pi by 2.
90 degree, right? Pi by 2. Okay, so you are getting 1.5707, which is same as math dot pi divided by 2. Okay, so if you want to find out the cosine inverse, you can write a cos. Okay, tan inverse a tan and so on. Okay, so did you get about the trigonometric operations?
Yes, sir.
Yes, sir.
Yeah, okay. And then if you want to compute a square plus b square, square root of a square plus b square, you can make use of the hypot function. Okay, find out the hypotenuse of a triangle whose side lengths are 3 and 4. So 3 comma 4, you get it as 5. Sorry, what was the error that I did here?
You didn't type math dot hypot.
Yeah, right. Math dot hypot of 3 comma 4. Okay, so if you want to find out the square root of a square plus b square, then you have to use math dot of hypot of a comma b. Okay, so that's another built-in function. Then we have functions for converting degrees to radians and radians to degrees. Okay, so let's see degrees function, math dot degree of math dot pi. Okay, so what did you observe? What does the degree function do?
It converts radians into degree.
It converts radians into degrees. Okay, if I want the reverse, similarly, math dot radians 90. Okay, so 90 is pi by 2, which is 1.57. Okay, so if we want to compute sine of an angle when we know that the input is given in degrees, then we can use this statement. Okay, so if I type math dot sine of 90, this will be wrong. Rather, if I want to find out sine of 90, I can write math of sine of radians, math dot radians of 90. Okay, so first the inner math dot radians converts 90 to pi by 2, and then when we apply sine on it, we get the result to be 1. Okay, execute this. Okay, so now onwards, if you want to find the sine of an angle where input is given in degrees, you don't need to do the conversion. You can use math dot radians to do the conversion on your behalf. Okay,
Yes, sir.
next. Okay, fine. Next, if we can even use this in our. So I want to find out the sine inverse and display the result in radians. How can I do that? Hmm? Sine inverse of 1 is 90 degree, but here I am getting it as 1.5 radians. Tell me, how can I make the result to come in degrees?
So maths dot degrees and then bracket maths dot
Try, try,
ASI.
try, try, try. Both of you try and see to that your result should be 90 degrees. Tanmay,
Yes, sir.
hello. Tanmay, are you there?
Yes, sir.
Okay.
Sir, can you repeat what you said? I couldn't hear you.
Why? Hello.
Sir, I couldn't hear you. Can you repeat that part again?
My question is, I want to compute the sine inverse of 1 and I want you to obtain the result in degrees.
So can
What
you repeat
instruction will you
the
write
degree?
for that?
Can you repeat the degree part?
I want the result to be in degrees. Okay, sine inverse of 1. Uh, Sine inverse of 1 is 90 degree. Okay, so write a instruction such that the output comes as 90.
Okay. 1 second, sir.
Disha, were you able to do it?
Yes, sir. I got it.
Okay, just wait. So to find that, if you find the sine inverse of 1, you are getting it in radians. Okay, and this result we have to convert it into degrees. So to write it as a single instruction, we have to write it as math dot degrees of math dot sine inverse of. Tanmay, what should I write at the end? Hello?
Yes, sir.
No. Tanmay. Tanmay, are you there? Hello? Floating point types. Okay. You can even do hexadecimal conversion of x. Okay, so let's see the value of f and s. So 14.25 written in hexadecimal will be this one. Okay, 1.C8000 into 10 power 3 or so on. Okay, then if you want to convert it back, you can use float dot from hex function. Okay, anyway, I will share all these instructions to you. You just need to repeat them. And again, you can reconvert it back to hexadecimal. Okay, the same way. Okay, and as I said, math comes with several uh, constants. Okay, you have math.py, math.e, and so on. Okay, you can explore those. E is your 2.718 and
Sir,
so on.
Tanmay texted in the chat. She's
Ah,
asking you to add her.
okay.
Sir, can you hear me now?
Yeah, yes, I can.
Yes, sir.
Okay. So we were looking at complex numbers. Okay. So Python provides complex numbers also. It should be of the form a plus ij, something like that. Okay. So a is equal to 3 plus 3 plus 4j. A, so this is how we can store complex numbers. Okay. So here, which is the real part, which is the imaginary part? Hello.
3 is the real part and J is the imaginary.
J is the four is the imaginary part. Okay. J is like your I that you write in your regular representations. Okay. So if you want to obtain the real part, you can just say a dot real. It will give you 3. A dot imag gives you the imaginary part. Okay, did you understand? Apply the type operation on A. Perform type operation on A. Tell me what is the result. Tanmay, you can hear me now?
Yes, sir, I'm doing.
Yeah. What instruction should we write here? How do you find the data type of A?
Um, Type and then bracket A.
Yeah, type A. Okay. A is of complex type. Okay, like earlier when we did f is equal to 2.3 and then do type f. F is of float type. Likewise, the value A in our case is of complex type. You can find the absolute of A also. Okay. What is the absolute of a complex number? Hello.
So I don't remember that.
Absolute is nothing but the sum of the squares of real and imaginary part, and finally we calculate the square root of it. Okay. So absolute of 3 plus 4j is 5. 3 square plus 4 square whole root. You square your real part, square your imaginary part, add them and find out the square root of it. 3 square is 9, 4 square is 16, 9 plus 16 is 25, square root of 25 is 5. Okay, that is called as the absolute value of a complex number. And you also have a conjugate operation. For every complex number, you have a corresponding conjugate. So to find out the conjugate of it, you have to type a dot conjugate or whatever number you have taken, a, b, whatever. Okay. So if a is 3 plus 4j, its conjugate is 3 minus 4j. Okay. Hello.
Yes,
Yes, sir.
sir.
Yeah. Okay. So this is with regard to complex numbers. So you can even write programs that have computation of complex numbers also in your programs. Okay. That's also allowed in Python. Okay. Yeah. Floats are inaccurate. I think I have an example. So, import decimal. First import decimal. Like import decimal. So as I said, always with regard to floats, you don't get the exact results, you get approximate results. You can see 1 by 3 is 0.333. In maths it's actually a recurring decimal, 0.33333 and so on. Okay, but here if I print the value of a, it is showing 0.333 up till certain digits. After that I'm getting different values, so it is only approximate and not accurate. Same way 1 by 6 b, when I display, it should have been ideally 0.1666666, but again after some particular decimal values you are going to get approximate, you're going to get wrong values. That's why we say that the floats are stored as inaccurate. But however, okay, this much amount of precision is fine for us for most of our computations, like 15 digits. Okay, after the decimal point, if we are getting correct values, anyway, even if there is error in this, we can neglect them because they don't make that much difference to the overall value. They will be still closer to the actual value. Okay, so that's why we say floats are actually inaccurate. Okay, so hmm. Then so we saw all these operators. Okay, the first one is the power operator, multiplication, division, integer division, modulo, plus, minus, assignment. So now when we have an equation which has multiple operators, the question is which operation should I perform first. So for this we have something called as the operator precedence. Okay, so in operator precedence, okay, to discuss operator precedence we have to also, okay, relational operators. Okay, anyway, these you know them. I think type conversions we have discussed all of these. Relational operators, this is lesser than, greater than, equality, inequality. Okay, so let me quickly show you. I is equal to 3, j is equal to 5. So what is I less than j? Is it true or false?
True.
True. Okay, you can see the result for yourself. I greater than j is false. So that's why they are called as a relational operator. They establish a relationship between I and j. So I less than j. So the result of which will always be a Boolean value. When you apply a relational operator, the result will always be a Boolean operator, true or false. Okay. So I is I equal to 3. You should read this double equal to as is I equal to j. Okay, not as j being stored into. Okay, let me write that. If I write I is equal to j, what is the meaning? Can someone tell me?
Uh, we're we're telling that I is equal to j, so the value of I will be the value of j.
Or we are saying assign the value of j to I. I is equal
Yeah.
to j. Copy the value of j into I. Okay. So here, if I use double equal to symbol, okay, you should read it as the equality operator. We are just performing a test of equality. We are checking whether I and j have the same values. So when I test for equality, again the result is either true or false. Okay, it gives a Boolean result. Okay, I is equal to j. What will be the result of I is equal to j?
False.
False,
False.
because 3 is not equal to 5. Okay, and we have an inequality operator also. Is I not equal to j? Is it true or false? Is 3 not
Uh,
equal to 5?
it's true.
True.
Okay, true. And likewise, I also have sometimes I want to test whether it is less than or equal to. Okay, in such cases, I can write I less than or equal to j, which is true. Okay, suppose say j has a value 3. I set it to be 3. Okay, I double equal to J. What is the result now?
True.
True. Because J value changed from 5 to 3. I already had a value 3. Okay. What about I less than or equal to J? Tanmay?
Sir?
I less than or equal to J. I is 3, J is 3.
True.
True. Okay, it is less than or, so we are saying less than or equal to. So if it is either less or equal to, we say true in that case. I greater than or equal to J. Okay. So these are the relational operators. Okay, this is uh, less than, this is greater than, less than or equal to, greater than or equal to. Okay. So now we studied relational operators, then we studied the arithmetic operators. Okay. We studied the assignment operator. We also studied the compound assignment operators. So we can write complex expressions which can involve all these expressions together, all these operators together. Now comes the question as to what is the order in which we have to evaluate these expressions. Okay. So for that, like how you have in your maths, the BODMAS rule, brackets first, division next, multiplication, followed by addition and subtraction, something similar. Okay, we have something called as the operator precedence. Okay, uh, I will share, anyway, I'm sharing this file. So we have written a table with several rows. So any operator that is at the top of this table or the chart has a higher precedence, means that that gets executed first. Okay, so it is unary plus or minus. So what we mean by unary plus or minus, plus and minus that are used for symbolic purpose. Okay, minus 3, plus 3. Okay, unary plus, it is working with only a single operand. Okay, so we take the unary minus to be executed first, unary plus or minus. Then next thing is, if there is any power operation, exponentiation, we take it for next. If you have a logical operation not, that has the next precedence. After that, you have multiplication, division, integer, and remainder operations. These have the same precedence. So now comes the question: what if I have a star b sorry, a divided b star c? In that case, we do a left to right execution because division and left multiplication have the same precedence. We will execute them from left to right. Whichever is first from the left, we will execute it. After multiplication, division, integer, division, and remainder operations, next precedence is for binary additions and subtractions. Relational operators have the next level of lower precedence. Okay, among them, first we check for this less than and greater than first, and later for equality or inequalities. After that, we have and, or, and so on. Okay, so let's take an example here. Okay, can you see this?
Yes, sir.
Okay, so now tell me how would this be evaluated? Okay, oh, I think one more that we forgot was, on top of everything, we have the highest is the parenthesis operator. Okay, anything within brackets have to be evaluated first. This is called as the parenthesis operator. Okay, so in this equation, what gets executed first?
4 plus 3.
Yeah. Okay, so now this, instead of 4 plus 3, what should I write here? What
7.
is the result of 4 plus 3?
7.
Now the equation becomes of this form. Tanmay, now tell me which operation is done next.
Sir, next we do the
So we have plus multiplication plus power multiplication minus. Which operation will we do next?
Equal.
Hmm? Equals has the least precedence. See, it is at the bottom.
Yes.
Okay. So this is our precedence table. So which one we do, the Disha?
Sir, exponential, 5 power 2.
5 power 2, 5 raised to the power 2. Okay, star has the highest precedence when compared to any other thing equal to plus star. If we refer to our table here, see, exponentiation is the top, okay, compared to others in our expression. So this gets evaluated as, what should I replace 5 star 2 with? 5 raised to the power 2?
25.
25.
25. Okay. Next, which operation is executed first?
Multiplication.
Out of the existing operators, equal to, plus, multiplication, subtraction, multiplication has the highest precedence. Okay. And then we have not one but two multiplication operations. So which multiplication operation is executed first?
The left one.
The leftmost one. Okay. So Tanmay, which is the leftmost multiplication that we have to perform now?
25 into 7.
25 into 7 is the leftmost multiplication in our program, in our equation. From left to right, which is the first multiplication are you encountering?
Okay, so I couldn't unmute. Can you hear me now? Yeah, so the
Huh?
leftmost would be 4 into 4.
Huh. 4 into 4 that gets executed, not 25 into 7. Okay, so this would be evaluated as, instead of 4 into 4, what should I write? What is the result of 4 into 4?
16.
16. Okay, now tell me which operation should I perform? 3 plus 16 plus 25 into 7 minus 1.
25 into 7.
25 into 7. Okay, because multiplication has the highest precedence. So next, 25 into 7 is, I think, 175. Am I right? 25 is
Yes,
200.
sir.
Yeah. Okay. Next, which operation is performed next?
Addition.
Which addition?
3 plus 16.
Plus minus have the same precedence. So we'll
Yes.
execute the first plus. So which is 19. Okay, 3 plus 16 becomes 19. Then we do 19 plus 175. Okay, and subsequently we subtract 1 from it. That is how the execution is defined. Okay, so I think we'll stop here for today. Pi operator. Okay, I think there is one. Oh, okay, one small program is there. Let's just quickly see it. Okay. I think these programs you can run on your own and see. I will share this just to show which operation is performed first and so on. Okay. Pi operators 2. Huh. Suppose I will highlight this. Tanmay, can you tell me which operation is performed first here?
3
Plus,
plus
less
2.
than, minus. Okay. 3 plus 2. Then after that,
5 minus 7.
5 minus 7, and later relational. Relational operators have a lesser precedence. So we first find out 3 plus 2. 3 plus 2 is 5. Then we find out 5 minus 7, which is minus 2. Is 5 less than minus 2? What is the answer?
Sir?
5 less than minus 2. 5 less than minus 2.
False.
The result will be false. 5 is not less than minus 2, so the result will be false. Okay. So I will just show you one of this. So the result, it prints it as false. Okay. So like that, you can look at the results. Other things, you can run this program and find the output for yourself. Okay. So let's stop here. So today onwards, we use this StreamYard. The usage of it is that